Fundamental network examples. Even in a very simple game, equilibria can be arbitrarily inefficient. For example, consider the prisoner's dilemma and let the player's costs in the Nash equilibrium tend to infinity. For every reasonable objective function, the objective function value of the unique Nash equilibrium is arbitrarily larger than that of the optimal outcome. Since the inefficiency of equilibria cannot be bounded in general, a natural goal is to identify classes of games in which equilibria are guaranteed to be approximately optimal. Fortunately, this is the case for a wide array of fundamental network models. So the section illustrates the concepts defined in section 17.1 by informally introducing 4 such models. Chapters 18 to 21 study these and related models in a greater depth. Selfish routing. We begin with a model of a selfish routing that is discussed extensively in Chapter 18. We introduced the model via Peagoose Example, which was first discussed in 1920 by the economist Peagoose. Example 17.1, Peagoose Example. Consider the simple network shown in figure 17.1. Two disjointed edges connect a source vertex S to a destination vertex T. Each edge is labeled with a cost function C dot, which describes the cost, that is the travel time, incurred by users of the edge as a function of the amount of traffic routed on the edge. The upper edge has the constant cost function C of x equals to 1, and thus represents a route that is relatively long but immune to congestion. The cost of the lower edge, which is governed by the function C of x equals to x, increases as the edge gets more congested. In particular, the lower edge is cheaper than the upper edge if and only if less than 1 unit of traffic uses it. We are interested in the price of anarchy of this game. Suppose that there is 1 unit of traffic representing a very large population of players, and that each player chooses independently between the 2 routes from S to T, assuming that each player aims to minimize its cost. The lower route is a dominant strategy. In the unique equilibrium, all players follow this strategy, and all of them incur 1 unit of cost. To define the optimal outcome, we assume that the objective function is to minimize the average cost incurred by players. In the above equilibrium, this average cost is 1. A simple calculation shows that splitting the traffic equally between the 2 links is the optimal outcome. In this outcome, half of the traffic on the upper link incurs cost 1, while the other half on the lower link experiences only half units of the cost. Since the average cost of traffic in this optimal outcome is 3/4, both the price of anarchy and the price of stability in this game equals to ratio 1 divided by 3/4, which is equals to 4/3. So general selfish routing games are conceptually similar to Peagoose Example, but are more complex in several respects. The network can be an arbitrarily large directed graph. Different players can have different source and destination vertices, and each cost functions can be arbitrarily non-negative, continuous, and non-decreasing functions. One property of a Peagoose example that holds more generally is that the price of anarchy and the price of stability are equal. That is, the average cost incurred by traffic is the same in all equilibria of the game. Chapter 18 proves this essential uniqueness property using a powerful and flexible technique called the potential function method. Roughly, a potential function for a game is a real valued function defined on a set of possible outcomes of the game, such that the equilibria of the game are precisely the local optimal of the potential function. Not all games admit natural potential functions, but most of ones discussed in this part of the book do, as we will see in chapters 18 and 19. When a game admits a potential function, there are typically consequences for the existence, uniqueness, and inefficiency of equilibria. One of the goals of Chapter 18 is to understand how the price of anarchy of a selfish routing game depends on different properties of the network. For example, recall that the price of anarchy in Peagoose example is precisely 4/3, thus bound degrade as the network size grows, as the number of distinct source and destination vertices increases, as the age cost functions become increasingly nonlinear. If players control a non-negligible fraction of the overall traffic, Chapter 18 proves answers to all of these questions. For example, in every network with a affine cost function of the form ax plus b, no matter how large and complex, the price of anarchy is at most 4/3. With anarchy arbitrary cost functions, even with the simple network structure shown in figure 17.1, the price of anarchy can be arbitrarily large. This will be in exercise 17.1. Network Design and Formation Games. Chapter 19 studies a diverse set of models of network formation and network design with selfish players. Here we discuss only one with the goal of illustrating the differences between the price of anarchy and the price of stability. We define a Shapley network design game as follows. Like selfish routing game, such a network design game occurs in a directed graph G. Each HE of the graph has a fixed non-negative cost CE. There are k players and each player I is associated with a source vertex Si and a destination vertex Ti. Player I wants to establish connectivity from its source to its destination, and its strategies are therefore the SITI paths of G. Given a choice of a path Pi by each player I, we assume that the formed network is simply the union for all Pi index I of these, and that the cost of this network is the sum sigma CE summing for OE, which is in the union I of Pi of the cost of these agencies, and we assume that this cost is passed on to the players in a natural way. The cost of each edge of the formed network is shared equally by the players who use it. More formally, each player I incurs cost CE/FE, the ratio for each HE of its path Pi, where FE denotes the number of players selecting paths that contain the HE. This defines a finite non-cooperative game, and we are interested in the inefficiency of the pure strategy Nash equilibria of this game. We assume that the social objective is to minimize the cost of the formed network. Example 17.1. Consider the network shown in figure 17.2. There are k players, each with the same source S and destination T. The age costs are k and 1 plus epsilon, where epsilon greater than 0 is arbitrarily small. In the optimal outcome, all players choose the lower age. This outcome is also a Nash equilibrium. On the other hand, suppose that all of the players choose the upper age. Each player then incurs cost 1. And if a player deviates to the lower age, it pays the larger cost of 1 plus epsilon. This outcome is thus a second Nash equilibrium, and it has cost k. The price of anarchy of the game in example 17.2 is roughly the number of players, and we review this as unacceptably large because we cannot control k. This example motivates the study of the price of stability of Shapley network design games. Recall from section 17.1.3 that the price of stability has a natural interpretation in network formation games. It measures the inefficiency of the network that a designer would propose to selfish players, i.e., the best equilibrium. The price of stability in example 17.2 is 1. The next example shows that this is not always the case. Example 17.3 HK example. Consider the network shown in figure 17.3. There are k players, all with the same sync t, and epsilon greater than 0 is arbitrarily small. For each I which is chosen among 1 to 3 until k, the age SIT has cost 1 over I. In the optimal outcome, each player I chooses the path SI to V to T, and the cost of the formed network is 1 plus epsilon. This is not a natural equilibrium, as player k can decrease its cost from 1 plus epsilon divided by k to 1 over k by switching to the directed path sk to t. Indeed, this directed path is the dominant strategy for the kth player. Arguing inductively about the players k-1, k-2, and so on until 1 shows that the unique Nash equilibrium is the outcome in which each player chooses its direct path to the sink. The cost of this outcome is exactly the kth harmonic number hk equals to sigma summing for all 1 over I, and I is the index starting from 1 to k, which is roughly ln k. The price of stability can therefore buy arbitrarily close to HK in Shapley network design games. So one emphasis on pure strategy natural equilibrium and example 17.3 motivate the following two questions. 1. Does every Shapley network design game possess at least one pure strategy natural equilibrium? Recall from example 1.7 that not all games have such equilibria. 2. What is the largest possible price of stability in a Shapley network design games? Chapter 19 uses the potential function method discussed in section 17.2.1 to resolve both of these questions. This method answers the first question in the affirmative and also shows that the price of stability in every k-player Shapley network design game is at most hk. In other words, for each value of k, the game in example 17.3 has the largest possible price of stability. Chapter 19 also discusses the price of anarchy and stability in other models of selfish network design and formation. Scheduling games. Our next example is a load balancing scenario, where the goal is to spread several identical jobs evenly across a number of identical machines. This is a very simple type of scheduling problem. This and much more general scheduling models have been extensively studied and have numerous applications. See Chapter 20. We focus on this special case to illustrate a non-utilitarian objective function makes the strategy Nash equilibrium and the interaction between the two. Concretely, we assume that there are m jobs and m machines for some integer m greater than or equals to 1. Players correspond to jobs. The strategy set of each player is the set of machines. Each player I seeks to minimize the total number of players, including I itself, and select the machine. This defines a non-cooperative game. The pure strategy Nash equilibria of this game are precisely the m factorial outcomes in which each player selects a distinct machine. There are additional mixed strategy Nash equilibria, as we discussed below. To study the price of anarchy, we require an objective function. Thus far, we have studied only utilitarian objective functions, where the goal is to minimize the sum of the players' costs. Here, motivated by the goal of load balancing, we focus primarily on the egalitarian objective of minimizing the number of jobs on the most crowded machine. This objective is called makespan minimization in the scheduling literature. The set of optimal outcomes under this objective coincides with the set of pure strategy Nash equilibria, and thus these outcomes all have a makespan equal to 1. In the previous two examples, we studied only pure strategy equilibria, where the objective function value of an equilibrium is clear. In the present application, we also consider mixed strategy natural equilibria. Such an equilibrium naturally induces a probability distribution on the set of game outcomes. Specifically, since we assume that the random choices made by distinct players are independent, the probability of a given strategy profile is the product of the probabilities that each player selects its prescribed strategy. We define the objective function value of a mixed strategy Nash equilibrium as the expectation over the induced distribution on the game outcomes of the objective function value of an outcome. Thus, the objective function value of a mixed strategy Nash equilibrium is its expected objective function value. As we now show, allowing mixed strategy Nash equilibria can increase the price of anarchy in scheduling games. Example 17.4 is a very common example called balls and beans. In the above example with M jobs and M machines, suppose that every player selects a machine uniformly at random. We claim that this defines a mixed strategy Nash equilibrium. To prove it, adopt the first player's viewpoint. See each of the other M-1 players chooses a machine uniformly at random. All M machines appear equally loaded. More formally, let Xij denote the indicator random variable for the event that player I selects the machine J. If the first player selects machine J, then it incurs a cost of 1 plus sigma Xij, summing for all I greater than 1. By linearity of expectation, its expected cost on this machine is 1 plus the sigma of the expectations of Xij, summing for all I greater than 1, which happens to be 2 minus 1 over m. Since this expected cost is independent of the machine J, every pure strategy of the first player is a best response to the mixed strategies chosen by the other players. As a consequence, every mixed strategy of the first player is also a best response. This argument clearly applies to the other players as well, and hence this set of mixed strategies forms a Nash equilibrium. When the objective function value of this mixed strategy Nash equilibrium, the expected value, what is that? What is the objective function's value of this mixed strategy Nash equilibrium? The expected values of the most heavily loaded machine. We emphasize that this expectations of the maxima chosen among all the set of sigma xij summing for index I is not the same as the maxima expected load. The maxima chosen among all index j of the expectations of the sigma of xij summing for all I, which is only 1. Intuitively, the expected number of jobs on the most crowded machine is governed by the severity of the collisions that occur when the players select machines in a randomized and uncoordinated way. This non-trivial problem, typically called the balls into beans problem, is classical and has been thoroughly analyzed. In particular, the objective function value of the above mixed strategy Nash equilibrium is theta of log n divided by log m. As m grows large, we can see the analysis in chapter 20, and also several classical papers for analysis of the cases about the optimal case of the balls and beans. Collisions due to the independent random choices therefore give rise to significant inefficiency. The price of anarchy with respect to the pure strategy Nash equilibria in this example is 1 for every m greater than or equals to 1, whereas the price of anarchy with respect to mixed strategy Nash equilibria is omega of log m slash log m as m grows large. Example 17.4 shows that the price of anarchy can depend fundamentally on the choice of equilibrium concept. Recall the fourth question of section 7.1.2. As an aside, we note that it also illustrates the dependence of the price of anarchy on the choice of objective function. Specifically, consider the utilitarian objective function, where the goal is to minimize the sum of the player's costs. The optimal outcomes, again, coincide with the pure strategy Nash equilibrium, and all of these have objective function value equal to m. The objective function value of the mixed strategy Nash equilibrium in example 17.4 is defined as the expected sum of the player's costs, which by linearity of expectation is the same as the sum of the player's expected costs. The calculation in example 17.4 shows that each player's expected cost equals 2 minus 1 over m, and thus the objective function value of this mixed strategy Nash equilibrium is precisely 2m minus 1. This is in fact the worst equilibrium of the game. You can try to analyze that in our exercise 17.3. And hence the price of anarchy for the utilitarian objective in this example is only 2 minus 1 over m. We could also consider the objective of minimizing the maximum expected load. Instead of the expected maximum load experienced by a player, both of these objectives can be viewed as egalitarian objectives, and they assign the same objective function value to every pure strategy profile. In particular, these objective functions have identical optimal values. However, they typically assign different values to a profile of mixed strategies. For example, the maximum expected load experienced by a player in the mixed strategy Nash equilibrium in example 17.4 is only 2 minus 1 over m. This is the worst equilibrium as in exercise 17.3 that we just mentioned before, and the price of anarchy with respect to the maximum expected load of a player is therefore only 2 minus 1 over m. An arguably undesirable feature of this objective is that the price of anarchy is small, even though, with high probability, the player's random strategy selections produce a pure strategy profile with objective function value omega of log m over log m times that of optimal. Returning to the make-span minimization objective considered in example 17.4, chapter 20 proves that thus the price of strategy is bounded above by big O of log m over log m in load balancing games with n jobs and m machines, even when the machines are non-uniform in a certain precise sense. Chapter 20 also studies the price of anarchy in several variants of the scheduling games. Resource allocation games. We next study a game that is induced by a natural particle for allocating resources to players with heterogeneous utility functions. Chapter 21 studies such games in much greater depth. We consider a single divisible resource, the bandwidth of a single network link, say to be allocated to a finite number n greater than 1 of competing players. We assume that each player I has a concave, strictly increasing, and continuously differentiable utility function ui. A resource allocation game is defined by the n utility functions u1, u2, u3 until un in the link capacity c greater than 0. An outcome of such a game is non-negative allocation vector x1, x2, x3 until xn with a sigma summing for all xi index I equals to c, where xi denotes the amount of bandwidth allocated to player I. We study the utilitarian objective and are thus interested in maximizing the sum sigma summing for all ui of xi summing for all index I of the player's utilities. The proportional sharing protocol allocates bandwidth as follows. Each user expresses its interest in receiving bandwidth by submitting a non-negative bit bi. The protocol then allocates all of the bandwidth in a proportion to the bits so that each user I receives xi equals to bi times c divided by sigma of bj, summing for all j index starting from 1 to n. Units of bandwidth. So that is each user I receives xi units of bandwidth, the formula we just give you, and the player I is then charged its bit bi. See section 17.3 and chapter 21 for 21st for a discussion of alternative particles that have a similar flavor. We assume that player payoffs are quasi-linear in the sense of section 9.3. In other words, the payoff qi to a player I is defined as its utility for the bandwidth it receives minus the price that it has to pay. That is, qi of b1, b2, b3 until bn is equals to ui of xi minus bi, which is equals to ui of the formula that we just derived before, bi times c divided by the sigma summing for all bj, summing for index j starting from 1 to n. Then after we send the utility functions out of this ui function, the value, then we minus bi. So assume that if all players bid 0, then all users receive 0 payoff. Our restrictions on the utility function ui ensure that the payoff function qi is continuously differentiable and strictly concave in the bit bi for every fixed vector b minus I with at least one strictly positive component, exercise 17.4. As usual, b minus I denotes the vector of bits of players other than I. An equilibrium is a bit vector in which every user bids optimally given the bits of the other users. Definition 70.5. A bit vector b1, b2, b3 until bn is an equilibrium of the resource allocation game u1, u2, u3 until un c if for every user I which is chosen among 1 to 3 until n, qi of bi and b minus I is equals to superior of qi of bi hat and b minus I, where bi hat are all those bi hat greater than or equals to 0, and we choose the superior. Potential function method also applies to resource allocation games. This method can be used to show that for every resource allocation game, every equilibrium bit vector induces the same allocation. Thus, every equilibrium has equal objective function value. The next example shows that equilibria in resource allocation games can be inefficient. Example 17.6. Consider a resource allocation game in which the capacity C is 1. The first user has the utility function u1 of x1 equals to 2 times x1, and the other n-1 users have the utility function ui of xi equals to xi. In the optimal allocation, the first player receives all of the bandwidth and the corresponding objective function value is 2. This allocation does not, however, arise from an equilibrium. To see why, observe that 17.1 implies that the only bit vector that induces this allocation are those in which only the first player submits a positive bit. Such a bit vector cannot be an equilibrium, as the first player can bid a smaller positive amount and continue to receive all of the bandwidth. See also exercise 17.5. A similar argument holds whenever the first player's speed is a sufficiently large fraction of the sum of the player's speeds. If the first player lowers its speed, its allocation diminishes, but the effective price per unit of bandwidth that it pays decreases by a large enough amount to increase its overall payoff. More formally, suppose that b1, b2, b3 until bn is an equilibrium, and let b denote the sum of the bits. By exercise 17.5, at least 2 of the bits are strictly positive. By definition, the bit b1 satisfies 17.3 since the payoff function q1 is continuously differentiable and strictly concave in the bit b1 and b minus 1 fixed. We can see that from exercise 17.4. Please practice. We can compute b1 by differentiating the right-hand side of 17.3 and setting this derivative to 0. Starting from the defining equation 17.2 of the function qi, using that u1 of x1 is equals to 2 times x1 and c equals to 1, and calculating, we obtained the condition 2 times b minus b1, then divided by b squared is equals to 1. For a player I greater than 1, the same calculation yields the condition b minus bi, then divided by b squared is equals to 1. Subtracting the second equation from the first implies that 2 times b1 minus bi is equals to b for every I equals to 2, 3, 4 until n. Adding these n minus 1 equations together gives 2 times n minus 1 times b1, then minus the value of the difference of b minus b1. Then that is equals to b times n minus 1. And solving this formula, we find that the first player's speed is only an n over 2n minus 1 fraction of the sum of the bits, and the b1 is equals to n times b. This is the total value of the bits divided by 2n minus 1. And in the resulting allocation, the first player obtains only an n divided by 2n minus 1 fraction of the bandwidth. As n grows large, roughly half of the bandwidth is allocated to the first player, while the rest is split equally between the other n minus 1 players. The objective function value of this allocation is roughly 3/2, which is roughly a 3/4 fraction of the value of the optimal allocation. Intuitively, inefficiency arises in example 17.6 because of market power. The fact that a single player receives the lion's share of the total bandwidth in the optimal allocation. Indeed, resource allocation games were initially studied under the assumption that no users have non-trivial market power. In this case, equilibria are fully efficient and the price of anarchy is 1. Details are discussed in the chapter 21st. Chapter 21st also uses the price of anarchy as a criterion for mechanism and particle design. We foreshadow this work in the next section.